So the usual way of presenting the proof of this involves a lemma. So when you have like P divides A times B, yeah?
P divides A.
P divides A or P divides B. Yeah? Okay? And so if you have that, right, and you also have like P1, P2, P3 equals Q1, Q2, Q3, right?
Mm-hmm.
That means P1, let's make it just P1, P2, yeah? So equals Q1, Q2, yeah? Okay, so you haven't missed anything. So then P1 divides Q1 times Q2, right?
Yeah. So P1.
So A could be Q1 and B could be Q2, yeah? So that means P1 divides Q1 or 2, but without loss of generality, just reorder them so it divides the first one, yeah?
This is a good prime. So
Yeah, so if a prime divides a prime, then it must be equal, okay? And the way we prove this lemma, okay, is to basically use that Bazoots lemma, remember? We have like ax plus by equals 1, remember? And if a and b are co-prime, then there exists x and y, yeah? So you just set, so you just let one of these be p, okay? So assume that p and a is co-prime, yeah?
There exists.
And there exists x and y such that this equation is true, okay? And if that's the case, then you can times. So the assumption is P divides AB, right?
Yeah.
Okay. You can times both sides by B. You get ABX plus P BY equals B, yeah?
Yeah.
So therefore P divides AB, P also divides this, so P has to divide B. Yeah? So if it doesn't divide A, then it has to divide B. So it has to divide A or B. Right? And then you can prove the fundamental theorem.
Yeah.
Okay. So that's the way you'd usually show it if you wanted people to learn the theory of this as well, right? But I thought so. But we were looking at this book the other day, and like,
I just read it.
It actually has a pretty cool proof in it.
Yeah.
Okay, so it avoids doing all this. Okay, it's actually pretty self-contained. So I want to go through that. Okay, and so if you missed the other classes, you can still understand the truth of this theorem. Okay, so it starts like this. Okay. So I'm following this number theory book by Hardy and Wright. So basically, call a number abnormal if it has two factorizations, two different prime factorizations, right? Call number abnormal if it has two distinct prime factorizations, yeah? Okay. And then let n be the smallest abnormal number, yeah? Does that make sense?
Yeah.
So n is abnormal means that you have like P1, P2, maybe like PK equals Q1, Q2, QL, yeah? For some primes, yeah? Okay. And anything smaller than n has a unique factorization. That make sense?
Yeah.
Okay, so this is the starting point of the argument, and apparently you can argue this all the way. Okay, so maybe I can break it down for you a little bit if okay, so the first claim is, can you show that none of the p's are equal to any of the q's? So So the first claim is no
Well, yeah, because then you can just
P.
divide. You can just divide n by the thing, and you get another abnormal number.
Any.
Yeah.
Yeah, because we're assuming that n is the smallest abnormal number, right?
Yeah.
But if one of the p's is equal to one of the q's, then we can just divide it by p, the thing, and n over the thing will still be a normal number because the rest will be different.
Yeah.
Yeah, and then after that we can prove that because of that, if we have that abnormal number, then the two numbers won't have the same factors. That's pretty cool.
It's not done yet. So there's no overlap at all between the P's and the Q's, yeah?
Yep.
Okay. And then we consider this number n equals little n minus P1, Q1. Okay.
What?
Let's see what that comes.
Wait, what? What do you mean by
So I define another n, yeah?
Yeah.
That's this n minus P1, Q1, yeah? Maybe you can tell me something interesting about big N. Okay?
Wait, n equals n minus p1.
what? This is kind of weird because it doesn't follow.
N minus p1 q1.
I mean, you can factorize it, right? Hold on, it's equal to. Well, okay.
Yeah,
Assume that. Assume that for okay. Make two subcases. One where we assume that. Okay. Idea.
Oh.
Alright. We have. Thank you. Okay, we have to wait, what? No, what did I do that? But then that means that P1. But then that means that n divides P1 and then divides Q1. Why don't we do this again?
Oh, so you're saying P1 divides big N, yeah? And Q1 divides big
Yeah.
N, yeah?
And since they're both prime, they have to be equal. Which is a contradiction.
Why do they have to be equal?
Oh wait, no, I'm done.
Alright, let me add some more details here.
Minus q1.
Okay, I guess I didn't specify the choice of P1, yeah? So we can let P1 be the smallest of the PI, yeah?
And Q1 is this one.
Q1 is the smallest of the QJ.
Was that L?
Huh?
It's L. Wait. Oh,
Q1
Smallest of the Qs, yeah?
Okay.
Didn't see.
Okay, so we know that n's composite, yeah, it's not prime. Yeah.
Yeah, obviously.
Yeah.
There's something else timesing n. And so we know, for example, P1 is less than the square of P1 is less than or equal to n, right?
Yeah.
That makes sense, right?
Yeah.
Kind of obvious. Same is true for Q1, yeah? Yeah. Okay. And I guess some kind of clever combination shows that actually P1 times Q1 is also less than or equal to N, right? That makes sense?
Yeah.
So this number actually makes sense. Because if it wasn't less than, it'd be like a negative number. Okay? So you take the smallest two primes, and you consider N equals N minus P1.
Yeah.
Okay.
You subtract.
Now what?
Yeah, and then you subtract P1, Q1 from N, yeah?
Mm.
So this is actually legitimately a positive number. Well, it's not 0. So this is actually strictly less than N, yeah?
Wait. Yeah. Because only one of them. One is smaller than the other.
Yeah. Actually, this should be every number greater than 0.
Well, no, because one can't be factorized because one isn't a prime.
Oh, it's an empty product. Like it has no primes appearing in its factors. Okay, so say something interesting about N now. Okay, so N is actually it's a number. It's actually a positive number, and it's less than little n, right?
Yeah.
So can you say something interesting about it?
It should also be a normal number.
I mean,
I mean, the
obviously
logical-
multiple of all of the others.
I mean, logically, we would just say that. I mean, logically, the proof is probably gonna somehow prove it as an abnormal number based on what we've said.
Well, what's like a really obvious thing we can say about capital N?
Well, it divides. I mean, P1. It divides T1 and Q1.
Oh, so we can say P1 divides N, right?
Yeah, Q1 also divides it.
Q1 divides N, yeah?
Yeah.
Okay, keep going.
Alright, consider N over P1 Q1.
Wait, big N or little N?
Big N.
That's
Or okay, so we've already assumed that P1 and Q1 are not equal, right? So
Yeah.
N over P1 Q1 is still an integer.
So N over P1. Yeah.
Q1.
Huh?
N over P1 Q1.
N over P1 Q1.
Yeah, because that's because the P1 and Q1 are equal and they both divide N, so that's still an integer.
Wait, so you're saying what you're trying to say is P1 Q1 divides N?
Yeah.
Is that true?
Because they're not equal yet.
Well, why does that not being equal imply that the product divides it?
Because it's prime.
but the product divides
Like having
because you have like the other all of the
Okay,
other
P1 and
primes,
Q1
right? And then you have all of the other primes. This is
Alright,
like
okay,
one
well
minus
so we're assuming that N is not an abnormal number, right?
which
Because
N?
Big N.
Oh, okay. Why didn't you say so?
Big N is not an abnormal number, which means that there is only
N
one.
is not. Why are we assuming this?
Because we've
the
already
smallest.
because N is the smallest abnormal number. So and we're subtracting something from it. So because N is less than big N is less than small N, right?
Yeah. So I guess we should have said smallest abnormal number greater than 0. Yeah. So and it is greater than 0. So it's greater than 0 and it's smaller than the smallest. So it must not be abnormal, right?
So and that means that P1 has one unique factorization, and P1 and Q1 are both in there, so it's gonna be whole if you divide.
Yeah. Does that make sense? So actually, capital N has a unique factorization, right? So if P1's in there, then it's just in there. And if Q1's in there, it's also in there. Okay? So it's in there, like in that factorization. So the product is also in there, right? That makes sense what I'm saying? So actually P1, Q1 divides N. Yeah? Okay, where do you go from here?
I have no idea. Demon.
Currently have no idea.
Michael, use
What?
your god powers.
Wait, hold on.
But you just got there by yourself.
But I don't want to.
Wait.
You're like done.
Yeah. So basically, in
Oh, okay, wait. Can you just tell us what we're trying to get to? Like, are we trying to get to a contradiction?
Well, that's the idea.
yeah.
I don't know what contradiction we can get to. The only one logical one is proving that n is not as abnormal number.
Wait, I skipped a bunch. I don't know.
Hold on, P1Q1 divides n, and n equals n minus P1Q1.
Yep.
Meow.
Therefore, the other. Wait, what? The other ones.
Okay. So we know that P1Q1 divides n, right?
Yes.
And we know that n equals n minus P1Q1, right?
Yes.
Yeah, so say that n equals k P1Q1, yeah?
Mm-hmm.
Then n equals k plus 1 P1Q1. Which means that P1Q1 are in its factorization, right? But that can't be because we're saying that there's 2 and they're not, and P1 is not equal to Q1, which is a contradiction. Therefore, we are not.
Oh.
Brain power.
Wait,
Huh.
what?
Did you understand what he just said?
I'm slightly.
It's always better when people prove it themselves from some point.
I feel smart.
Have the big brain.
Yeah.
Wait, it's like KP1Q.
I mean,
This is K plus.
Okay, so basically, do you want to see? So what is do you understand what he wrote there? Yeah. So he essentially wrote that P1 Q1 right divides little n. Yes.
Yeah.
Okay. Why is it a big deal that little P1 Q1 divides little n?
Because P1 isn't equal to, well, because there are different prime factorizations, which means that there's only one.
Yeah. So. Yeah. So if P1 Q1 divides n, right, then they appear in the same prime factorization. Why is that?
Q1 divides.
Big. Because if they don't, it wouldn't make sense.
Yeah, so I guess that's part of this. So it's actually much easier to get prime factorizations than to get unique ones, right? To get a prime factorization, you just have to keep factoring out primes, right? It gets smaller and smaller. You'll be done eventually, right? So here, if P1 Q1 divides n, then P1 Q1 times something else equals n, right?
Yeah.
And that something else can be prime factorized. Yeah?
Yes.
You can even say it could be prime factorized uniquely, right?
Yeah, it has to be prime factorized uniquely.
Because it's not abnormal, yeah?
Exactly.
Yeah.
So there's actually only one way to extend this to a prime factorization, yeah?
Which means there's only one.
Yeah.
So
Which
it
is
gives
a contradiction.
yeah. So there's lots of ways to get a contradiction here.
Wait, what was the purpose of big N?
The big N.
Yep.
The big N was there to force P1 and Q1 to both divide N at the same time, like as a product, not just individual.
As a product.
Yeah. So I mean the big N. Okay, you need to use the assumption that it's the smallest, and big N uses the assumption that it's the smallest the most.
I like this.
Yeah. So there's lots of ways to finish this.
Thank you. under free. It was like,
Yeah, so and the fact that P1 and Q1 both appear in the same prime factorization of n is a contradiction, right?
yeah, because
Because we said no P is equal to a Q, yeah? But one of the P's is equal to one of the P's here. Or one of the Q's, yeah?
Wait, hold on. So,
So if you want to be even more explicit about it, okay? So you have like, so you have that Q1, right? Divides n on P1, right? See that?
Q1 divides
Because P1 Q1 divides n, yeah? So that means if you
Q1 divides n,
yeah, if you cancel out the P1,
which means that
then Q divides n on P.
divides n, but then that means that the thing.
Yeah, but what is n on P1, right?
Yeah.
So n on
Just
P1.
n remove P1.
Yeah, look at it. It's P2.
Q1 must be in there.
It's this, isn't it? Yeah? Not only is it this, it's only this. Because there's only one factorization, right? Not only is it this, it's only that, right? And now if Q divides that, okay? That means Q has to be one of them because it's a unique factorization, right?
Mm.
But the hypothesis said that P's were not equal to any of the Q's. You see the contradiction?
Yeah.
It's kind of neat, huh?
Would you say that it's like if there's a smallest factor of n, which has to be prime obviously,
Which
then there's a smallest factor of n, and if they're all distinct,
which n? Little n.
like little n, yeah, if they're all distinct, then one of them has them and one of them doesn't. But then if the other one doesn't, then it would form n.
Yeah. Yeah. Yeah, so you take the smallest one and cancel it out,
Yeah.
you'll get all the other ones times together. And that's unique. Oh, any questions about that?
That was cool.
Yeah, kind of a new way to prove it, right?
That's not what you're saying?